Good morning, students. Today we are entering into 12th class. First lesson electric charges and fields. Very important topic for the NEET exam. Each chapter we have divided into, as usual, into concepts. Concept is followed by minimum 12 to 15 problems. Our intention is you will get the in-depth knowledge about the concept and how to apply it in various conditions. So it is advised that in our channel, target JE also there, target CET is also there. There also same chapter will be there. So another 15 questions you can go there, and another 15 questions you can also watch in CET. So minimum in a particular concept you will get 30 problems, 30 various problems, different model problems. So whatever the study material you will follow, at least you can do 90% of the models problems. If any doubts get and any problems you are not able to do it, so you just post us to the WhatsApp number given in this channel. So you for that and also you mention your name, so we will post the answer solution in our channel in Students Hub with your name. Student Hub is dedicated for the doubts of the students. So like that you can make use this channel. We are giving very quality lectures in this channel. Let us see today's chapter is electric charges and fields. In that today we are going to discuss about the concept electric charges and Coulomb's law. So within this framework, whatever the very important concepts often asked in the NEET examination, we'll discuss. After that, this content lecture is followed by the solved problems. In this, whatever the content we have discussed, in that content only, we'll going to do some problems, minimum 12 to 15 problems. We are going to do it. Okay, right. Let us start learning this concept, electric charges and Coulomb's law. First of all, let us discuss about basics. What are the basics about charge, electric charge? See, electric charge. So, what is the electric charge? This is a basic property of matter. So, this is the intrinsic property of a matter charge. So, materials made up of atoms. In atoms, positive nucleus and electron is revolving around it. Nucleus is having positive charge and electron is having negative charge. So, every material is having these charges. So, basic property of a matter is a charge. So, how much value we have to take a charge? So, basic charge is equal to charge on electron. So, basic charge we will take as a charge on electron. Why? Electron is a stable particle. Many subatomic particles are there. They are also having charge less than electron also, but they are not stable. So, electron is always stable. That is one advantage. Another advantage is whatever the speed this electron moves, the charge quantity, the magnitude of the charge it is having, never that value changes. That's why we have taken the charge on electron is a basic charge, and it is easy to transfer this electron from one metal from one body to another body. That's why we have taken it as a basic charge. What is the charge on electron? Electron charge is 1.6 into 10 to the power of minus 19 coulombs. Coulomb is a SI unit of the charge, and the nature of charge on electron is minus. We know that two types of charges are there, positive and negative charges. This property of a charge having two different minus and plus charges, this different properties it is having the charge. This property is called the polarity, positive polarity, negative polarity, like that we take. Okay, this is the basic charge. Another one, these points we have to remember. So charge symbol often we use a small q. So charge formula it, I is current, t is the time. So dimensional formula, so dimensional formula is at at. So dimensional formula is at at. One more point we have to remember is charge is a scalar. So charge is a scalar. Scalar means it is having only magnitude, number. So charge is a scalar. So these points you have to remember. Let us move on to next discussion. This is frictional electricity. In your lower classes, you might have come across the frictional electricity. This we can produce by friction. So, if two bodies you take and if you rub it, one body transfers it electron, one body, see this body is having electrons, this body also having electrons. So these are the materials. So if you make a rub both of them, if you rub, because of thermal energy, valence electrons, the electrons which are moving in outermost orbital of atom, they will get the energy and they will come out of the atom. So see, when we are making friction like this, we are rubbing the both surfaces of a material. One material transfers electron to the other material. Which material transfers the electron? Which material takes the electron? The material which is having less electron affinity, it will lose the electron, it will give away its electron, and the particular material which is having more electronic affinity, it will receive the electron, it will take the electron. So whenever you rub two different materials, charge transfer takes place. Here this material having less electron affinity, so it loses the electron, it transfers the electron. So as it is lose the electron, number of electrons in this surface of a body decreases. So this body we say it is positively charged, it acquired positive charge. This body which is having more electron affinity takes the electron from this material. This body is having negative charge like that, because excess of electrons are there on the surface of this body. Like this, lack of electrons means positive, excess of electrons is negatively charged body. So charging a body, what we mean, charging a body is adding electron or removing the electron or adding the electron is called charging. So here by friction, see, suppose for example I have taken a glass rod. This is a glass rod I have taken, and this glass rod I rubbed with a cloth. This cloth is a woolen cloth, or it may be a silk cloth. So if I take a glass rod and I rub with a woolen cloth, fur or silk cloth, what happens? This glass is having less electron affinity. So it transfers electron to this woolen cloth. So it is some, for suppose for our discussion sake, it lost 6 electrons. That's why it is 6 positive charges it is having. These 6 electrons went here onto this surface of a cloth. That's why this became, after friction, after rubbing, this glass rod turns into positively charged body, and this silk cloth turns into negatively charged body. So this is what happened in frictional electricity. So what we came to know, charging. Charging means adding or removing electron. So that is called charging. So next we'll discuss about how this charge is detected in primary, uh, how this charge is going to be detected. Just now we came to know how to produce charges by friction, what is the meaning of charging and all these things, what is polarity. Now, how to detect. So, primary detector is a gold leaf electroscope. How it works? See, it is having a brass circular disc connected with a copper. This is a copper. This is brass disc, and a copper rod will be there at the end of the copper rod. Two gold foils will be there. Gold foils are very, very, very thin, so very lightweight. So whenever charges come, because of their charge, they will repel each other. So this all the arrangement is placed inside a bottle. This is vacuum chamber. So what happens if vacuum chamber is not there? If some air is there, air ionizes. It also takes the electrons from the gold leaf. So if electron is some charge is leaked out, we cannot detect, measure the quantity of charge. That's why we always take this arrangement in a vacuum chamber. Let us see how it works. So I brought a positively charged body. This is a positively charged body. I touched this brass disc with this positive charge. I have taken a positive charge and I touched this one. Immediately, what happens? Positive charges will be transferred to the brass rod. Whenever the positive charges are transferred, copper is a good conductor of electricity, so all positive charges goes and positive they repel each other. Because of the repulsion, these gold foils will have some angular displacement. By calculating the angular displacement, we can determine the quantity, the magnitude of charge here on the body. Like this, we can detect and we can also measure the electric charges. What if the positive charged body is not touched? So when the body is not touched, see what happens. The body is not touched. What happens? Because of induction, the positive charge, just I brought the positive charged body near to a brass cylinder, brass disc. What happens? Opposite charges will be induced on this brass charge. So whatever the positive charge remaining in this material, it will go to the gold foil, and the angular displacement separation between these two gold foils we can calculate. By calculating this theta, we can also calculate the magnitude of charges. So like this, the gold leaf electroscope works in detecting a charge. What type of charge also we can estimate, but we cannot completely know what type of charge we have given. One thing, if positive charge is brought near to the brass, no contact, negative charges, positive charges will be separated because of induction. and like this. If I remove this, if I take back this charged body, then what happens? Immediately, these positive charges and these negative charges, once again, they will recombine, and there shall be no there shall be no angular displacement because they recombine each other. These positive negative separated because of the positive charge. But when the positive material is positive charged body is touch with this brass rod, then what happens? If you remove it also, it will be showing the same displacement. So to discharge, to neutralize this instrument called gold leaf electroscope, you have to uh, uh, you have to touch with the negatively charged body. This is how the gold leaf electroscope works. In frictional electricity, what we came to know, if any uncharged body rubbed with another body, one body gets positively charged, another body gets negatively charged. That's why we have taken a body and we have made a friction. So with a woolen cloth. So glass rod, woolen cloth. We made a friction. Because of the friction, electrons transfer from this body. So 1, 2, 3, 4, 5, 6 positive charges are there. So I may say the charge on A, I take a glass rod as a having plus 6 coulombs of charge. Just for discussion's sake. Coulomb is a very big unit. That's why we want to use coulombs always in the practical things. Very small quantity of charge is enough. Micro coulomb, nano coulomb, milli coulomb only we use. So we get a QA is equal to plus 6 coulomb. It has transferred 6 electrons. So this woolen cloth I will take as a body B. It is having minus 6 coulombs of charge. So after friction, just for discussion's sake, we have taken on the glass rod plus 6 coulombs are there, on on the woolen cloth minus 6 coulombs of charge is there. So after friction, opposite charges are developing because of this. After we make a, see, before that these two bodies are having no effect. When we rub, this body becomes positive, this body becomes negative, they will attract each other. Why? Because the like charges repel each other, unlike charges attract each other. So after friction, these two bodies will attract each other. See, one thing, when I am talking about production of charge, don't misunderstand, we cannot produce charge. Right here, charges we not produced. These electrons are transferred here. That's why we are seeing positive charge on this body. We are seeing negative charges on the body. We are not newly created. We can the electrons can be distributed, redistributed, so that we can get positive charge and negative charge. Let us take conduction. In conduction, this body I have taken. This is body A. This is another body I have taken. This is body B. Two bodies I have taken. This body I have given some positive charge. So 8 positive charges I have given. So the charge on A is equal to plus 8 coulomb. 1, 2, 3, 4, 5, 6, 7, 8 coulombs. Here in the initial stage, B carries no charge. Now what I did, I made a contact. So what I did, I made a contact. So when I touch the positive charge with a body having no charge, what happens? The positive charges start flowing from one body to another body till the total charges, the both on charges, they will share equally mean charge will be there on both of them till the charge will flow from charged body to uncharged body till the potentials become equal. So how it happens? See, if I made a contact and I separated. This is A, this is B. Then what happens? 8 are there. So now it is having only 4. It is having 4. So after contact, what happens? Charge on A became 4 Coulomb and charge on B also became plus C. So what happened? Here equally they shared the charges. This is called conduction. So after conduction, what happens? Both bodies acquired same type of charge. This is also positive, this is also positive. Same quantity of charge. This is also 4 Coulomb, this is also 4 Coulomb. So after, see, before conduction, these two bodies are not attracting. After conduction, both bodies having same type of charges, so they repel each other. They repel each other. So they repel each other after conduction. In the frictional velocity, they will attract each other. So like this. Once again, we'll have a suppose this QA and QB both are charged. Both are charged. I'll write like this. This is body B. This is body A. Both are having charges. QA is having charge Q1 positive. QB body B is having charge plus Q2. Both are having charges. Previous in example, one body is having charge, another body not having charge. By just making a contact, the electrons, the charges transferred. That's why both became having same type of charges. Both are having equal charges. Now here one body is having charge Q1, another body is having charge 2. See, previously one body is having plus 8 Coulomb, another body is having 0 Coulomb. So total net charge is equal to 8 Coulomb. That is shared by two bodies. That means 8 by 2 Coulomb. So plus 4 Coulomb. So both bodies are having plus 4 in previous example. Now both bodies having charge. So if both bodies having charge, then the net charge is equal to Q1 plus Q2. Each body have charge Q1 plus Q2 by 2. They will share. So suppose for example, this body A is having charge plus 8 Coulomb. This body B is having charge plus 4 Coulomb. They made a contact. Whenever two bodies are made into contact, the charges will flow from one body to another body. The body having more charges, it will from this body A to B, the charges will flow. Here the body having more charges means more potential it is having, less potential it is having. So high potential to low potential, the charges will transfer. Like that the conduction takes place. So how much? See, after contact we separated the both bodies. This is A, this is B. So this is A, this is B. We separated both the bodies. Then what happens? Net charge plus 8 plus 4. How much this is? 12 Coulomb plus. So after that the formula is Q1 plus Q2 by 2. So 12 by 2 plus 6 Coulomb. So it is also having, A is also having plus 6 Coulomb, B also having plus 6 Coulomb. Like that, the charge redistributes in a conduction. One more example, let us see. What if this body is having plus 8 Coulomb, this body is having minus 4 Coulomb charge they are having. Now these both bodies are made into contact so that the charge will redistribute, charge will flow. Then after conduction, what happens? See, this is body A, this is body B. Here, net charge plus 8 minus 4, that is equal to 4 Coulomb. What is the polarity of this one? Plus 4 Coulomb. So Q1 plus Q2 by 2. So 4 by 2. That is equal to 2 Coulomb. What kind of charge it is? Plus 2. So if two bodies get into contact, after that A body is having plus 2 coulombs of body, B also having plus 2 coulombs of charge. So this thing, from this small discussion, what we came to know is in the conduction, after conduction, both bodies acquire same type of charge, both bodies are having same magnitude of charge. That's why in conduction always bodies will repel whether both bodies are having same charge, both bodies are having different type of charges, or one body is charged, another body is not charged. In all these three examples, we came to know that after conduction, both bodies acquire same type of charge, same magnitude of charge. After conduction, these two bodies will repel each other in the conduction. Third one is induction. So induction, in this induction, there shall be no contact of bodies. See, this body is there. This is the body B. It is not having any charge. I brought near a body B having charges. So a charged body brought near, not made a contact, just brought near to uncharged body. Then what happens? The opposite charges will induce in a body. This is called induction. So if I bring, this is body A. Body A of having plus 4 coulombs of charge, then body B, it becomes a minus 4 coulomb of charge. So here type of charge is different, quantity of charge is same. So after induction, in induction what happens? Opposite charges will come, same amount of charges will come, but the type of charge is different. After induction, these two bodies attract each other. So in frictional electricity, after friction, two bodies get different types of charges. Both are having different same type of magnitude, and they will attract each other after friction. In conduction, both bodies having same type of charge, same amount of charge. They are having both same charges, so they repel each other. In the induction, both are having same quantity magnitude of charge but type of charge is different. After induction they will attract each other. What if I have taken a charge plus q, I brought near to a sphere, to a sphere. Whenever we bring near a charge on the body, in both the in between them, the induction takes place. Because of induction, see the face near to towards the positive is get negative charges. The surface which is away from this positive charge will get positive charge. Once I removed, then what happens? These positive charges, these negative charges, both will recombine. Then charge net charge is equal to once again 0. We are discussing about distribution of charges. So if we charge a body, what happens? See, if you go in depth, materials are two types. One is conductor, another is insulator. Conductor, another is insulator. Conductors, insulators. What is the difference, main physical property of these conductors and insulators? Conductors, they conduct the electrons. Electrons are having freedom to move everywhere, one side to another side inside the conductor. The restriction of flow of electrons will be there, flow of charges will be there in insulators. So generally conductors are metals. Non-conductors are non-metals. The non-metals like the glass and others, these non-metals, amber, non-metals are insulators. Mainly all metals are good conductors. Let us give charge to a conductor. I have taken a conducting rod. I have taken a conducting rod. I have supplied a charge. So all the charge resides on the surface of the conducting rod. So total charge I want to calculate. Then what I have to calculate? The linear charge density. Linear charge density. So whenever charge spreads, distributes along the length, then linear charge density we have to calculate. What is the symbol for linear charge density? Lambda. Formula is charge per length. SI unit is Coulomb per meter. This is linear charge density. If I take conducting lamina, a plate, conducting lamina or a plate I have taken. In the plate what happened? Area is dominant and thickness is very very less. If I give charge to this, all charges will distribute on the area of a this kind of body. So I have taken conducting lamina or metal sheet I have taken. I given charge. On the area, the charges spread. Why? Thickness is very less. So here we have to calculate aerial charge density. So aerial charge density symbol sigma is equal to charge by area. SI unit Coulomb per meter square. Now, if I take a three-dimensional object, so conducting sphere I have taken. I will write here. The insulator later we discuss. So I have taken conducting sphere. So this is one dimensional body, two dimensional body, three dimensional body. If I give, this is a conducting sphere. If I give charge to the conductor, so charge I have given to a conductor, but charges repel each other. It is a conductor, charges can move freely in a conductor. Then what happens? All the charges will reside on the surface of a conductor. So if you give charge to a conductor, inside they won't. Why? They repel each other. They can move. That's why freely they repel, and they will be distributed on the surface of a conductor. Always, if you give a charge to a conductor, charge resides on the surface of the conductor. As charge is residing outside the body, inside the body, if you take the electric field, this is 0. Outside the body, electric field is not 0. Why outside? Charges are there. So here also, even though this body is three-dimensional body, the areal charge density only we calculate. So areal charge density. So let us take, this is the radius of this sphere. Then charge density sigma is equal to formula charge by total charge. I will take as capital Q by what is the surface area of a sphere? 4 pi r square Coulomb per meter square. Like that, even though it is a three-dimensional body, the areal charge density only we calculate. Why? Because inside the charges never reside. What if this is about conductor? What if non-conductor we have taken? Non-conducting rod, not a problem. All charges in one dimensional body, they will spread on the surface. Non-conducting sheet, all the charges they will reside on the area. So areal charge density you can calculate. So conductors and insulating bodies, when we give charges, they will stay there only, they cannot move. So linear charge density, areal charge density, same to same. But if I take a non-conducting sphere, three dimensional, one dimensional, two dimensional, same thing, but three dimensional, non-conducting. If I take non-conducting sphere, then if I give charges, charges will spread all over the non-conductor. Why? Because whenever you give charges, they cannot move from one place to another place. Even though repulsion is there, they cannot move freely in a non-conducting body, non-conducting material. So they stay there only. That's why what we have to calculate here, volume charge density. We have to calculate volume charge density, not the areal charge density. So volume charge density only comes into effect, you have to calculate for non-conducting 3D objects only. Why? Because inside also charge is there. As charge is inside, so inside electric field is not 0. Outside also electric field is not 0, because outside also charges will be there. All over the body charges will be spreading. Anyhow, volume charge density we calculate only for non-conducting 3D objects. So formula is, the symbol is rho, quantity of charge Q by volume. So how charge distributes in a friction, conduction, induction, how charge distributes in a non-conductors, in conductors we discussed, but regular bodies only we have taken. How? Why? See, if I take irregular conducting body, see, I have taken a body like this, irregular conducting body. So if I take a body like this and given charge, then what happens? See here, this surface can be imagined as a part of a circle. This radius is R1, this is the center of the radius. This surface also we can imagine as a part of a circle. This radius is R2. It is a conducting surface. Charges will reside on the surface. So I have given the charge. More charges will see, more charges will be here, less charges will be there. So if you consider irregular conducting body, wherever the radius of curvature is less, more charge will accumulate there. Wherever radius of curvature is more, less charge will be accumulating. This is how the charge distributes in a irregular conducting bodies. So here charge is more, here charge is less. So surface charge density is inversely proportional to radius. What is this? Radius of curvature. Radius of curvature is less, more charges will be accumulating. When radius of curvature is more greater, then less charges will accumulate on this body. This property of charge is used to safeguard the lightning from skyscrapers and all. Even on the top of a police stations, you can see this is a skyscraper. So in rainy season, sometimes this lightning will come. So when lightning is of having full of charge. So from the top of the from the clouds, the charge sees where is the less radius of curvature, so that they can accumulate. So if there is a big free space, this is a playground, so nobody there. See from the top, the skyscraper is having less area of curvature. Though all this lighting will fall onto the building, and building will be smashed and it will be under fire. So how to safeguard here? One copper umbrella they will place. Copper umbrella. This copper umbrella area surface radius of curvature is very less. Here radius of curvature is very more. So this lighting will come here. This is connected to ground. So all the excess charge will go into the ground. Like this, skyscrapers, police stations, and important buildings will be safeguarded from the lightning by the using the property of charge. Charge always accumulates wherever the radius of curvature is less. Like this, charge will distribute on conducting and non-conducting bodies. Next our discussion is properties of charges. In this first property we call it as polar quantization. See, any physical measure changes in equal steps, in equal proportions, we call it as a quantization. Here, charge always quantizes. See, if you take a body like this, I have taken a body, I have taken one body. If I give a charge, what is charging? Charging means adding electrons or removing electrons. Now I want to charge it. So if I give one electron, so one electron charge. If we give one electron charge, only one electron charge will come. So here charge of this body 1 electron into electron charge. Electron charge is 1 into 1.6 into 10 to the power of minus 19 Coulomb. This is the charge we have given to this body. If I further supply electron, two electrons are there, then charge is equal to 2 into electron charge. So 2 into 1.6 into 10 to the power of minus 19 coulombs. If 3 electrons, if I give to a body 3 electrons of charge, so that is 3 into E charge, that is 3 into 1.6 into 10 to the power of minus 19 coulombs. In between values, in between charges, we cannot charge a body. See, in a step 1 into 2, 2 into electron charge, 3 into, in a equal steps, the uniformly the charge increases or decreases. If we remove the electron, in same manner, in same steps, it will decrease. If we give an electron in same steps, the charge on this body, how much charge this body is possessing, Q is equal to 3 electrons into each electron charge. Like that, if n electrons we have given to this, if n electrons of charge given to the body, so Q is equal to n electrons into charge of electron. So this is charge on electron. So this is the total electron, total charge on this body. So like this, n is a integer. N is a integer. So this is called quantization of charge. So charge on a body always in steps increases or in steps decreases. If we give electron, it is negatively charged. If you remove electron from a body, then it is positively charged body. It becomes like this. The charge always quantizes. See, suppose for example, I want 1 coulomb of charge. Coulomb is the SI unit of charge. If I want to give 1 coulomb of charge, how many electrons I have to supply? See, if I am supplying the electrons, the charge of the body go on rising. Right here, 1 coulomb charge I want. So how many electrons I need? So how many number of electrons I have to give to a body so that the charge on the body becomes 1 coulomb. So charge of each electron is equal to 1.6 into 10 to the power of minus 19 coulomb. So our formula is equal to Q is equal to Ne. Like this only the charge increases or decreases on a body. So N is equal to, we don't know, Q is equal to 1 coulomb. So N is equal to, I will do N is equal to Q by E. Q is equal to how much? 1 coulomb. This is 1.6 into 10 to the power of minus 19. So that is equal to 1 by 1.6 is equal to 6.68 into 10 to the power of 18 electrons. So if I supply these many electrons to a body, the body get 1 coulomb of charge. This is the meaning of quantization. Charge invariant. See, if electron is moving with tremendous velocity, also the magnitude of charge 1.6 into 10 to the power of minus 19 never changes. So the quantity of charge never changes with velocity. Next, third one is the charge is a scalar quantity, so we can add. So charge is additive. So if 10 charges are there, all charges magnitudes you take, you add, that is the total charge of the system. This is quantization. So quantization means charge on a body is integral multiple of charge on electron. Charge on body is the integral multiple of charge on electron. Charge on a body is always integral multiple of charge on electron. That is quantization. Invariant. So invariant means with velocity the magnitude of charge never changes. Next, additive. So charge is always additive. See, in a region, one region I have taken. In this region, plus 1 coulomb charge is there, plus 8 coulomb charge is there. Here minus 3 coulomb charge is there. Here plus 2 coulomb charge is there. Here minus 6 Coulomb charge is there. Like that, various charges are there. So, what is the net charge here? So, net charge. So, these are all not having any direction. That's why just we, as a numbers, we will add. How we add? See, 1 Coulomb. This is 8 Coulomb. This is 2 Coulomb. This is minus 3 Coulomb. This is minus 6 Coulomb. See, the type of charge, if it is negative, we are writing negative. If it is a positive, we are writing positive. So, this is called adding. So, charge is additive. In a region, these many charges are there. This region having how much net charge means just we adding. So, 8 plus 1 9, 9 plus 2 is 11 Coulomb, minus 6 plus 3 is 9 Coulomb. So, the remaining charge is 2 Coulomb plus C. So, plus 2 Coulomb of charge is there on this in this region. So, like this, simply if plus is there, plus we write, minus is there, minus is right. So, like this is called the additive. This is called the additive property of charge. Next, our discussion is Coulomb's law. Coulomb's law says that if two electric charges are there, this is plus Q1 charge, this is another charge plus Q2 charge, the distance between them is R, then these are like charges. That's why the charge 2 will repel charge 1 in this direction. So this is a force acting on first charge due to second charge. This is the direction of force acting on Q1 charge. Q2 charge also repelled by Q1 charge. See, Q2 charge repelled by Q1 charge in this direction. This is the force on second charge because of first charge. These are the directions of forces. Whether these two are positive charges, they repel. One is positive, one is negative, they will attract along the line. So, these two forces, see if I take this is Q1 charge plus Q1, this is minus Q2 charge, this is the distance between them are same, but unlike charges, so this q1 minus q2 charge attracted the q1 plus q1 charge will be attracted in this direction. This is the force on first charge because of second charge, and this minus charge is attracted by the first charge, that is the force on second charge because of first one. See whether they are like charges or unlike charges, whether they repel or whether they attract, then this force direction is always along the line joining the two centers of the force. See here also, see this is the line joining the two centers of a charge. This is the line which is joining two centers of the charge. So whether the both charges are repelling or attracting, this repulsing force, this attraction force, both are acting along the line joining the centers of the charges. That's why this Coulombian force is a central charge, central force. So what we say, Coulombian force, force is a central force. Coulombian force is a central force. It always acts along the line joining the centers. Let us go through the statement of Coulomb's law. Coulomb's law says that whether it is a repulsive force or attracting force, the force acting between two charges is directly proportional to the product of those two charges, and secondly, The force of repulsion or attraction between the charges is inversely proportional to square of the distance between them. Here we have considering a vacuum or air is there between the charges. If that is the case, what is the case? In between the charges, vacuum or air is there. That is the case. Then this force, see, this proportionality, if you want to remove, one constant must be there. That constant is F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. So this is the Coulombian force. It may be attracting in nature or repulsive in nature depending on the types of charges which are participating. That's why here the force, SI unit of force is Newton only. Here one term came, this epsilon naught. This epsilon naught is called permittivity. This permittivity is a property of matter. See, in between charges, vacuum air is there. That's why this epsilon naught I have written. Epsilon naught is permittivity of free space. Free space means the permittivity of vacuum or permittivity of air. So that is epsilon naught. This is a property of a matter. What is permittivity? Permittivity is a property of matter which allows the electric field lines pass through it. What are the electric field lines? We know na? When we take a positive charge, electric field lines normally they spread all over the space like this. So electric field lines are spreading around the positive charge like this. If it is a negative charge, electric field lines will be in this direction. So these electric field lines should be permitted to travel from Q1 to Q2. So in between vacuum is there, some material is there. So that medium is property is the permittivity of free space. So here one small point we can note it. See, permittivity came, that is a property of a medium. That means what? The force, Coulombian force, depends on the medium between the charges. Now, once again, so permittivity of the free space, F naught is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. This is, let us give, this equation is 1. So when vacuum and air is there, that is the formula. If some medium is there in between, then formula becomes Fm is equal to 1 by 4 pi epsilon naught will not be there. Now epsilon, so medium permittivity is into Q1 Q2 by R square. This is equation 2. So equation 1 by equation 2 if we do, we get, see, this epsilon naught comes down and epsilon m goes up. Epsilon m by epsilon naught, right? See what we came to know, epsilon is equal to epsilon naught epsilon r. This is the medium permittivity. This is epsilon naught. This is the vacuum or air permittivity of free space. What is the value? 8.85 into 10 to the power of minus 12 Newton meter square per Coulomb. Sorry, Coulomb square per Newton meter square. This is a permittivity. So here free space permittivity. Now, if I write epsilon r, is equal to epsilon m by epsilon naught. This permittivity is also called as dielectric constant. Dielectric constant, right? So dielectric constant K is epsilon m by epsilon naught. Now same thing here is there, see. So this is also epsilon r, this is also K. So in some problems these formulae are very very important. Let us write the vector form of Coulomb's law. See here, at once if you observe this diagram, this is in positive direction, this force in negative direction. So first observation what we do, what we write is F21 is equal to minus F12. So one force is acting on one body, opposite force or same magnitude of force is acting on another body. Magnitudes of forces are same, equal, but directions are different. And these two forces are acting on two different bodies. So these forces are action, reaction forces. So these forces acting on two bodies is action reaction forces. So Newton's law action, every action there is an equal and opposite reaction. So Newton's third law it will follow. So this is the one point. Second point, let us write the vector formula. F bar is equal to 1 by 4 pi epsilon naught q1 q2 by here. See 1 to 2. So if I write for Coulombian force on 2 because of 1 or 1 because of 2. So 1 because of 2, then R is equal to 1 because of 2 into R cap. So this is the vector formula. If not, we can also write this formula like this. So writing 1, 2, if you confuse, you just remember the formula like this. 1 by 4 pi epsilon naught q1 q2, here square is there, r square into r cap. In bar if you want to write, f bar is equal to 1 by 4 pi epsilon naught q1 q2 by r cube into r bar. Be careful. Why here r cube came? Because r bar r cap is equal to r bar by r. Like this you remember. Right? So r bar is r cap is equal to r bar by r. So r bar if I write, one more r will come, so it becomes r cube. These are the vector forms of the Coulomb's law. See, Coulomb's law is having some limitations. What are those limitations? Write the limitations. This Coulomb's law is applicable if charges are point charges. Charges should be point charges. Means very very small. And charges should be in rest. Charges should be in rest. If charges are moving, we cannot apply Coulomb's law. If charges are not point charges, we cannot apply Coulomb's law. Why? Because see, I have taken a big bodies. This is A, this is B. See, if both are having positive charge, See, this is the distance between them. Right? So, because of the repulsion, see this surface is very near, this surface are far away. So when these surface are near, these spheres are conductors. That's why what happens, these positive charges, because of repulsion, they will go back, they will go. That's why the distance, real distance, the is a different. Resultant distance between the charges will vary. That's why we cannot use. See, what is the real charge where the charge is accumulated? You cannot calculate. Why? Because they went away from the center. That's why the distance between charges is not r. That's why it is only applicable for point charges. When do we can apply for the big bodies? See, if this is the radius of a sphere, let us think that these two are similar spheres. If and only if r is very much less than small r, we can apply Coulomb's law. Can apply Coulomb's law. If not, we cannot apply. If they are very near, r value is comparable with the small r value, then we cannot apply the Coulomb's law. These are the limitations of Coulomb's law. Let us conclude our discussion about Coulomb's law. When there is no medium or air is there, then the force between the charges is different. When there is a medium between the charges, force between the charges is different. So the Coulomb's force depends on the medium between the charges. When there is no medium and only vacuum or air is there between the charges, then this force will be maximum. So see, let us write the formula F naught. F naught means between the charges vacuum or air is there. Then the formula is 1 by 4 pi epsilon naught Q1 Q2 by R square. This R I also give a symbol R naught. That means distance between the charges when vacuum or air is there between them. So this is equation 1 we take. This value 1 by 4 pi epsilon naught value, we give a symbol for this value small k. That value is 9 into 10 to the power of 9 Newton meter square per Coulomb square. So that is its value. So we can also write this formula. We can remember like this. F naught is equal to K Q1 Q2 by R square. Like this also R naught. So it is not necessary write F naught R naught, but keep it in your mind. If any medium is there between the charges and some medium is not there between the charges, if that kind of comparison comes, then you have to use this symbols so that it will distinguish this is for only vacuum and air. So if medium is there between the charges, then 1 by 4 pi epsilon of medium, permittivity of medium, and q1 q2, this is the r distance. This r distance is when medium is there between the charges. So this formula we can write like this: epsilon m, so permittivity of medium is equal to epsilon naught into epsilon r. So this is a permittivity of medium of medium. This is permittivity of free space. Free space means permittivity of vacuum or permittivity of air. This is known as relative permittivity. So these are the names. So see, here we can write like this: force between the charges when some medium is there between the charges, 1 by 4 pi. This is the permittivity of medium. So in this place I can write epsilon naught epsilon r into q1 q2 by r medium square. So this relative permittivity is also known as dielectric constant K. So I can write this formula like this: Fm is equal to, in the place of relative permittivity, I can write K. So 1 by K, 1 by 4 pi epsilon naught Q1 Q2 by R naught square, because this value came here. So we can write like this. So Fm is equal to F naught by K. So like this also we will get the result. This is equation 2. This is equation. So for air, vacuum, K value is equal to 1. K also denoted as, also called as relative permittivity. For metals, K is equal to infinity. If this is Q1 charge, this is Q2 charge, this is the distance between them. In between, vacuum, all air is there. Then F naught value is maximum. This is Q1, this is Q2, this is R. In between, non-metal. Non-metal means some glass slab is there. Glass slab is there between the charges. Then force for the glass or non-medium is there. Force is equal to F naught by K. So if this is Q1, this is Q2, this is the distance between them. In between, metal is there. In between, metal is there. Metal K is equal to infinity. So F is equal to 0. Like this, the force between the charges changes with the medium between them. Suppose, for example, Q1 is the charge, Q2 is the charge, between them vacuum is there. So distance I have written as R naught. So force between them in this case is 1 by 4 pi epsilon naught Q1 Q2 by R naught square. Now this is Q1 charge, this is Q2 charge. The distance between them are, because some medium is there, then force becomes Fm is equal to 1 by 4 pi epsilon naught of the medium into Q1 Q2 by R square. If the both forces are equal, if vacuum is there, this is the expression. If medium is there, this is the expression. In spite of placing medium between the two charges, if these two forces equal, if Fm and F naught both are equal, then what happened? I will write the formula for Fm. How? Like this: 1 by k, 1 by 4 pi epsilon naught q1 q2 by r square. That is equal to, because this r is different, F naught formula I will write 1 by 4 pi epsilon naught q1 q2 by r naught square. So be careful while using this formula. So I will cancel whatever the common things on both the sides. So this 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught cancels, q1 q2, q1 q2 cancels. Then 1 by k r square is equal to 1 by r naught square. That implies k r square is equal to r naught square. So relation between r and r naught, r is equal to r naught by root k. So this relation is very important. So if both charges are placed in this distance, even though some medium is there between them, the force when vacuum there between the present between the charges, and the force when medium is there between the charges, both forces equal if the distance between the charges in medium is equal to r naught by root k. Let us move on to equilibrium. Suppose two charges are there, plus q1, and at a distance plus q2, two charges are there, both are positive charges. Then the distance between them is r. Let us put at the middle. I will give some names: A, B. At C, I kept a small charge, that is also positive charge, some amount of charge. This is exactly at the middle. So this is r by 2 distance. So if these three charges are in equilibrium, what happens? See, this plus charge will repel this plus charge in this direction, and this charge will repel this charge in this direction. If these two forces are equal, then this plus q charge remain there only. So these three are in equilibrium. Now we have to check whether this equilibrium is stable equilibrium or unstable equilibrium. For that, what we do, I just moved this charge towards q1 charge an x distance. Then what happens? See, when this charge is moved towards q1 charge comes very near, so the repulsive force between small q and capital Q1 is great, so it will be pushed off onto other side. When this charge goes to this side, then it comes near to plus Q2. This is also plus, this is also plus. Like charges repel each other. Because of repulsion, it goes to this direction. Like this, it oscillates, and finally it come back to its mean position, its previous position C. That's why the if plus Q and plus small q and plus q2, all three positive charges are there. This line, a line passing through the line joining the, this is called axial line. This name of a line is axial line. A line joining the two charges is called axial line. So along the axial line, if you disturb a positive charge, if positive charge is in between two positive charges, it's when you disturb it once again after oscillation, it come back to its your mean position, its previous position. That's why along the axial line, if three positive charges are there, the stable equilibrium exists. For three positive charges, stable equilibrium is along axial line. Let us check what happens if Q is displaced in this direction. If I displace in this direction x distance, then what happens? See, if this charge is moved like this, let us take this charge came here, right? Plus q, small q. Then what happens? This plus q1 will repel this charge into this direction, and this also plus q2 repel this charge into this direction. So both directions are away. When two forces are acting on a point, the charge moves in the resultant force direction. So it will go away. Here also, if plus charge is there, this charge will repel this one and this charge will repel this one. So the charge will move in a resultant force direction. So it will be deflected away. So it will go away. It won't come back. That's why along the, see, if for three charges are positive charges, stable equilibrium along axial line. Unstable equilibrium along this line is called the equatorial line. So if three positive charges are there in equilibrium, then stable equilibrium lies along the axial line, unstable equilibrium lies along equatorial line. If you disturb like this, it will be deflects away, it won't come back. What if two charges are there? This is plus q1 plus q2, same thing, and distance between them is r. So this place I have given name A, this is B, exactly at the center. So this distance is r by 2. I placed minus q now. Previously plus q I have given, now minus q I have given. Now if I see, positive will attract this negative towards it. This positive q2 attracts this q1 towards it. That's why where these three charges are in equilibrium, they are not moving. But whether this equilibrium is stable or unstable, let us check. For that, what we have to do? We have to disturb that charge. So first, what we do? I will move this charge like this to x distance. Here I moved x distance. Here also I moved this like this in x distance. Then what happens? The negative charge, negative q, come closer to positive. That's why it attracts towards it. It won't leave it. It won't go to that side. No oscillation. So when you disturb this equilibrium along the axial line, so this minus q charge plus q charge, distance between them became small, less, so more attraction force is there. So this minus q will come onto the plus q. So if it is not returning to its previous position, that kind of equilibrium we call it as a unstable equilibrium. So if minus q is there at C, unstable equilibrium along what this is axial line. So if you disturb, it won't come back to its mean position. It will be attracted towards this Q1. So the along the axial line, the system is unstable equilibrium along the axial line. What if this minus q is moved like this x distance? So this minus q came here. This positive charge will attract this negative charge. This positive charge also attacks this negative charge. So negative charge will come back. And if it goes here, then also this will attract towards it. This is also attracts towards it. It will come back. So what happens if we just disturb like this? It will oscillate and finally slowly it comes to its original position, mean position. That's why if plus q minus q plus q, three charge system is in stable equilibrium along the equatorial line, unstable equilibrium along the axial line. This we have to note. So stable equilibrium along equatorial line. So along axial line unstable, along equatorial line it is stable equilibrium. This is about equilibrium of charges. So another kind of equilibrium state we'll discuss. See, this is a rigid support. Two bobs, two pith balls are suspended with non-conducting string and both balls given some charge plus q, here also plus q. Then because of repulsion, these two are separated a distance r. If I draw a perpendicular bisector, this angle is theta by 2. This total angle is theta. So what are the forces acting on this? See, This positive charge will repel this positive charge in this direction. This is Coulombian repulsive force. As Bob is having some mass, weight of a Bob acts in this direction. In the string, tension is acting. These are the three forces acting on this one. See, these two charges are in equilibrium because of repulsion, they stayed there only. So, on this charge, what are the forces acting? The repulsive force in this direction, the weight and tension in the string. Suppose this is the theta 2, so tension in the string can be resolved into components. So this is theta 2. So this is, see, theta 2 is adjacent, t cos theta 2. So in this direction, t sin theta by 2. These are the components of tension. So this F is equal to T sin theta by 2, mg is equal to T cos theta by 2. So all forces cancel away. Net force on this bob is 0. That's why it is there in a equilibrium. So let us write F is equal to, that implies F is equal to T sin theta by 2, mg is equal to T cos theta by 2. So from these two we can write F by mg is equal to tan theta by 2. By using these expressions we can calculate theta by 2 and the charge and the tension, weight, force, everything we can calculate if one physical quantity is given. What if the whole like this whole arrangement is drowned, is placed in some liquid? So let us see, this is a rigid support, this is a non-conducting strings, conducting spheres, this is positive charge, this is also similar positive charge, and they are repelled, and the distance between them is r. I have drawn a perpendicular bisector. Then this is angle is theta by 2. Right. So same this whole arrangement we are putting in a liquid. Then what happens? So we are putting this, see, kept in a liquid of density rho L, liquid of density rho L. Whenever the system is drowned, kept in a liquid, the weight of the bob changes. How? See, the G will change like this, 1 minus rho L by rho S. So in class 11, we came across this equation, how the G value changes. As G value changes, the weight also changes. As weight changes, then the new weight is equal to mg into 1 minus rho L by rho S. This is the only difference when this body is kept in the a liquid. This is the solid density. This bulb is made up of a solid, so this is having solid density. Liquid is having liquid density. So here same equations come, but in the place of mg, you have to take mg dash. I think you understood all the concepts discussed so far. This lecture video followed by solved problems, 12 to 15 problems in these concepts only, whatever we have discussed. Like that, every concept followed by solved examples. So you watch that video also and solve the problems as many as you can do with your study materials. If you get any doubts, just let us know. You post it in our WhatsApp number given below.